And good morning, guys. So we will continue with module one, chapter three. So we will have a short recap. The last class we actually saw what was Amdahl's law. We studied about speed up, and based on that we also saw some metrics uh, on arithmetic mean and harmonic mean, and in that we saw Amdahl's law. So Amdahl's law is nothing but you're just finding out a generic harmonic mean, and in that, what you're assuming is you have two phases in your problem. Okay, so first phase is completely a sequential phase, and the other one is completely parallelizable phase. So the sequential phase takes alpha fraction of the time, and the remaining 1 minus alpha fraction of time is going to be completely parallel. Okay, if that is the case, when you apply your harmonic mean and you find the speed up, you get this formula. Okay, 1 divided by alpha by 1. So and this is for sequential execution. The rate of sequential execution is 1, and rate of parallel execution is n. Okay, so this is the formula. So if you rewrite it, it's going to look like this. Okay, n divided by 1 plus n minus 1 alpha. So what it says is if you just assume your algorithm profile will look something like this. Okay, so this is like alpha portion, the fraction of the time where it is completely sequential, you cannot do anything about it. And then so there is this part where this 1 minus alpha percentage of time, it can be parallelized. Okay, so parallelized to n. Now when you find speed up, or when you increase the machine size, if you actually make it grow, like if you add n processing elements to it, then your speed up will be improved only for this fraction of your program. Okay, so only for this 1 minus alpha fraction of your program you are going to achieve some speed up. The remaining one, you cannot achieve speed up. Okay, so that's what your Amdahl's law says, and it's very, very important. Okay, and this is just a plot with different fractions of your sequential part. Okay, so ideally, when you have a perfect parallel algorithm which does not have any sequential part to it, then you will get this 45 degree line that says your speed up will be same as the number of processors you have added. So if you have 4 processors, your speed up will be 4x, and if you have 1000 processors, your speed up will be 1000, right? So that's what Amdahl's law says, but that's only on the ideal case. But we always have some overhead, and there is always the sequential part of your program, and because of that, you will always be lesser than 1 by alpha. Okay, so 1 by alpha is the speed up that you will get in any day, given alpha is the percentage of your sequential problem. Okay, sequential program part. Any questions on this, guys? Like I said, Amdahl's law is one of it's the heart of your computer architecture. So even in interviews, interviewers may ask this. Okay, so just keep in mind this. I mean, you don't have to remember the formula, but you just have to know the concept here. Okay. Now, based on this, right? So based on Amdahl's law and a few other metrics that we saw, we are going to see a few more extended metrics. Okay, so if O of n be the total number of operations by an n processor system, in other words, this is going to be your parallel algorithm. Okay, and if T of n is the execution time in steps. Okay, so we are going to take these two notations, and then we are going to say that T of n is going to be lesser than n O of n. Okay, so and then we assume T of 1 is equal to O of 1. Okay, so when your problem size is 1, then you assume the T of 1 time taken is going to be T of 1. Okay, so if you assume all these, then we are going to have a speed up factor It's going to be T of 1 divided by T of n. This we already know. Okay, so speed up factor is going to be the old execution time on a uniprocessor system divided by new execution time in the with n processor system. Okay, the enhanced processor system. Okay, so it's your speed up factor. Then you also have something called redundancy and utilization. So redundancy is it says that how much your algorithm makes use of redundancy, like how parallel can it become. Okay, so that is given by the ratio of O of n by O of 1. Okay, so that's your R of n. And then you have something called as utilization. And utilization says how much, like out of n processors you have, how much are you making use of. Okay, so that is nothing but R of n times E of n. Okay, E of n is your efficiency. Okay, so how much efficient you are. So when you so to get what E of n is, so we will find out E of n is nothing but your speed up divided by the theoretical maximum speed up you get, or degree of parallelism, right? So how much, if my algorithm, if I my sorry, not the algorithm, if I increase my uh, uh, system machine size by n, then theoretically maximum what will I get, right? So my alpha is equal to 0, so that's my theoretical max I can achieve. So it's going to speed up of n, correct? So that is what my theoretical max is. So efficiency is nothing but your speed up of n divided by n itself. Okay, so when you substitute that, then you get the formula for utilization. And finally, you have quality of parallelism. So quality of parallelism is directly proportional to your speed up and your efficiency, and inversely proportional to your redundancy. Okay, so we won't go much deeper into this, but just note these are different metrics that we will use to measure our parallelism in your architecture. So we just take hypothetical workload. Okay, so you somehow have found out that your workload has these metrics. Okay, your speed up is n plus 3 by 4, your efficiency is n plus 3 by 4, and so on. Okay, so you have somehow you have calculated all these things. Then when you plot it with the number of processors, right? So this is what you're going to get. Okay, on one y-axis you have efficiency and utilization, and the other one you have S of n, R of n, and quality Q of n. Okay, so this is how the plot goes. So it seems very complex, but the idea is simple. Okay, you can see a trend. Okay, if you just take let us say speed up, as you can see, speed up when you have only one processor, you start from like a zero speed up, because there is nothing, we're not parallelizing, and then as you proceed, as you increase, your speed up is also increasing. Okay, so which is a good trend. Okay, so your speed up should also increase when you increase the number of processors. And here this 45-degree line is the ideal speed up. Okay, that's when your alpha is equal to 0. Now this gap gives you the overhead. It could be because of communication overhead, or it could also be because of the ability of your program, right, to become parallel. So that is the gap. And similarly, you have all the other curves too. So we can just go over it, and then you can study how the algorithm behaves on this particular processor. Now, based on these different metrics, right? So, scientist Jack Dongara, so he has come up with a list of processors. So, see, he started rating these systems. Okay, so what he did was he took one algorithm. So, this parallel algorithm was to solve linear equations. Okay, you take linear equation, 1,000 linear equations with 1,000 unknowns. Okay, so linear equation, right, like y equals to a1 x1 plus a2 x2 so on, plus c. Okay, so that's a simple linear equation. Okay, so when you have to find out what is x1, what is x2, then you need uh, as many equations as you have the number of variables, correct? So if you have three unknowns, then you need three equations. So that's the linear equation problem. So and it's a classical problem to solve using parallel computers. Now, what he did was he developed this algorithm. He took the, I mean, not he developed, he actually took the standard linear equation solving algorithm, and then he ran it in different supercomputers, and then he started rating it. Okay, and this is what he obtained. Okay, so actually there's more to it. So we will see that in a couple of slides. Next, moving on. So we saw about linear equations, right? So linear equations is one of the standard problems that many of the applications use. But apart from that, we have something called as benchmarks, and typically we use two synthetic benchmarks that are very popular in supercomputing domain or in computer architecture in general. Okay, so one is Drystone, and this is one of the standard benchmarks that is in use even today. Even when you want to, it doesn't matter what computer you're working on. It could be a massive supercomputer, or it could be your cell phone. Okay, starting from that supercomputer range all the way down to your PCs, laptops, servers, and down to your cell phones. Every place where they develop a processor, where they design and develop a processor, they are going to run Drystone and measure its performance. Okay, but what does Drystone do? So Drystone is actually a synthetic benchmark, meaning it's not a real application. So it just has like uh, uh, it's synthetic, meaning like you just dump certain functions for, I mean, for random purposes, just to make it computation intensive. That's all. Okay, there's no actual meaning out of it. It's not a proper application. Okay, and Drystone is a integer performance benchmark, meaning there are only integer operations and there are no floating point operations. Okay, so there's no floating point here. And so basically the Drystone is mostly it has string operations. Okay, many of the operations it has is string. It has string concatenation, string division, and then and various other combinations of that. Okay, and it reports a score. It tells you k Drystones per second. Okay, based on that you can say this is my performance. And these days you actually measure your performance in dmips. It's called Drystone mips. So they call it dmips. So I have this much dmips, that much dmips. So I can actually Google it out to find more. Okay, so that's about Drystone. So there's something called whetstone. Okay, so historically whetstone preceded Drystone. Okay, so whetstone is actually based on supercomputer of the same name, which was given a code name based on location in somewhere in Europe. I believe it's somewhere in Great Britain, that part only. Okay, so that's why they gave that supercomputer Whetstone, and they used a synthetic benchmark to evaluate that computer, and they named that metric also, that benchmark also, as Whetstone. Okay, so interestingly, Drystone was developed later. So Whetstone has floating points in it. Okay, so it's a synthetic floating point performance measure. Uh, so, so when they wanted to have a synthetic benchmark parallel to Whetstone, they developed Drystone. Okay, so they named it a Whetstone with floating point, right? So when you remove float, that wet becomes dry, correct? So they named the other benchmark as Drystone. It's very silly, but just a trivia for you guys. Okay, so that's why you have your Whetstone and Drystone benchmarks. So anyway, so whetstone is also a synthetic benchmark, and here the unit is k whetstones per second, and this is only for floating point. And apart from that, we have transactions per second and k libs, kilo logic inferences per second. So these are the other two performance measures that you have. Any questions on this, guys? Next, we move on to the other topic, parallel processing applications. Okay, so whatever we are discussing, again, it's not about the general I mean everyday applications we use. Okay, whatever we are going to deal in this subject, it's not like YouTube or it's not Chrome browser. And there are other synthetic, I mean there are other standard benchmarks like zip, bzip, gzip, Those are some of the standard benchmarks we have. These are the frequent operations we use in daily life, right? Like as a normal user. But the applications we are going to deal with are massively parallel applications. Okay, and here they are called as grand challenges, and these are going to deal with several interdisciplinary challenging problems. Okay, so even in your textbook they use Fortran. Why? Because Fortran is one of the most popular languages even today for non-computer science field which involves computation. All high performance computing field that is not core computer science, they use Fortran. For example, computational fluid dynamics or weather prediction, all these things, right? So they still use Fortran. So for first example here we have is magnetostatic applications. So here you study the magnetic field, and the other second one is rational drug design. So we nowadays we are using artificial intelligence for drug discovery, right? So these are when you want to so these are very computation intensive. Okay, so that's one problem, and the other one is designing high speed aircrafts. So again, as I said, this will involve computational fluid dynamics. So where you're going to study aerodynamics of your aircraft. So, in that line, right? I also wanted to say something. So when I did my PhD, so I in Iowa State, so I had one of my friends who worked in aerospace department, and they were studying tornadoes. Okay, it was a very interesting project. So they had actually had a tornado generator. It's one of the biggest tornado generators in the world. So they could actually create a tornado in a lab. Okay, so there's a very big lab, and they create a tornado, and then they used to throw in sensors into the tornado. Okay, that they have generated. Have you seen the movie Twister? It's something like that. Okay, in Twister they do it for a real tornado, but here they create a tornado inside the lab, and they throw these sensors, and they actually model the tornado, and based on that they will actually study how to build houses. Okay, so how to make your roofs sturdy so that even when you have a tornado, your roofs will not fly off. Okay, so what are the pressure points that you need to focus on your roof? So these are some of the challenging problems that we are dealing with today, and you cannot do it on your laptop. Okay, so these require massive supercomputers. And again, we have quantum models for catalyst study. So that's another important. So not only for catalyst study, right? So there are a lot of quantum models that we are studying, and very interesting field. And again, ocean modeling. So how the so not only ocean modeling, there's also seismic waves prediction, right? So there are so many other things related to that too. And in addition to that, we have medical diagnosis, computational modeling for air pollution, protein structures. This is very, very important. So nowadays we are all seeing hybrid vegetables, right? And then hybrid varieties of crops. One example again I can give you is a hybrid variety of corn. So you study the protein structure of this corn, and then you are going to play around with it, and you're going to say what breed will give you better corn. Okay, so it's not only for eating. Okay, it's also for several other like drug discoveries, and there's also for they use corn for uh, ethanol, right? So corn based fuels are there. If you're not known so far, right? So there are from corn you actually get petrol. Okay, so that's something that some research is going on. uh, and there's also image processing and education field where there are so many applications that that are computation intensive. So this is like a general graph that says, I mean, how much computation your application requires. So as you see, like oil reservoir modeling and all, they're all like very small scale problems. Whereas when you go for structural biology and then like human genome and fluid turbulence and all other problems, it's really grand challenging. You need teraflops. and this teraflops is we're talking about 1992 here. Okay, and we have crossed teraflops. We are in petaflops region, like 10 to the power 15 floating point operations per second, and we are actually moving towards exaflops. Exaflops is 10 to the power 18 floating point operations per second. So it's actually it has grown big. So the main idea is to exploit massive parallelism in the applications. So, so most of these grand challenging applications have redundancy, right? So there are a lot of independent modules in the algorithm that you can exploit. So, because most of these are represented as matrices. Okay, so that's the main reason. So even the linear equations problem, if you take, if you have n linear equations, you represent it like a matrix, correct? You can solve it using a matrix. So most of these are matrix involved, and the very good thing about matrices, why did we learn matrices, right? You would have had this question in your engineering math. So we learned we learned matrices in maths because there are lots of applications that deal with this. Okay, so many of the grand challenging applications involve matrices, and good thing about matrices is that you have parallelism. Most of the matrix operations are can be independently done. It can be scaled very well. Okay, so here there's something called as instruction parallelism and data parallelism. So instruction parallelism is something like when you how many instructions can you execute parallelly, right? So here we saw some dependencies where two instructions are using the same data. Okay, so there you have data level dependency between two instructions, and there's the other parallelism called as data parallelism. So this views the entire problem as data. So which data I need, and then it's this is not instruction focused, but it's more data focused. Okay, so again there is a data dependency, everything comes in picture here, but again this doesn't deal with the problem as instructions, but rather problem as data. So this is the data I need, whether I have whether this is a valid data or not. The past and future of massively parallel processors. So one of the first supercomputers is our Iliad 4. It has 64 processing elements or 64 processors. This was in 1968, actually close to when we actually went to moon. Okay. I think we went to moon in 1969. Now, more recently, we have in 2020, we have Fugaku in Riken Center for Computational Science in Japan, and that's the world's fastest supercomputer as on date, and it runs at 500 petaflops. Okay, 500 petaflops is it's actually a big number. It's peta is 10 to the power 15. Okay, 500 into 10 to the power 15 floating point operations per second. Like I said, we are actually reaching exaflops range. Okay, so this is the world's fastest supercomputer. In comparison, in India, we have Pratyush. That's the fastest supercomputer in India. It's an Indian Institute of Tropical Meteorology in Pune, and it is ranked 23 in the list, and it runs at 4 petaflops. Okay, so 4 into 10 to the power 15. It's a very it's a massive it's a very fast machine. Okay, so maybe with comparison to Fugaku, it may look like it's a small number, but still this is actually a huge computing resource that we have. So if you want more information, you can go to top500.org. So Jack Dongora, as I said, he started it all. Okay, so he started ranking these supercomputers, and so based on that, you have the world's fastest supercomputer every year being released. Uh, Actually, they release it twice a year, I think. So one in July and one in December. Okay. So so this is according to the July report. July 2020 report. And yeah, so this is your Pratyush supercomputer. So we have a long way to go. So if we are currently ranked 23, okay. So I mean, I would have expected, like, if you just took 504, 500 is rank 1. When you say 4 petaflops, I would expect something in hundreds, right, rank. But you see how we are in rank 23. So it means, I mean, it's like only a few of these, probably in the top 10, are like they have the greatest, I mean, the fastest supercomputers. So most of them are good with the four to other range, right? Smaller ranges. Okay. So now application models, right? So I mean, the scalable computers and scaled problems. So this is like, there are two things that you have to scale. One is the computer. Okay, when you have a computer, like I said, if you buy a supercomputer or a cluster with 100 processors, and next year you plan to extend it, you buy another 100, then you'll have to add these together, right? So, or 1,000 processors, you have to add that to make like one big computer. So your computer should be scalable. The other thing is your problem itself, the problem that you are choosing, and that should be designed in such a way that it is also scalable. Then you have efficiency curves that we saw in one of the earlier slides. And next is application models. So application model. So we will see this in more detail in tomorrow's class probably. But here there are three things that we need to note. One is fixed load model. Next is fixed time, and next is fixed memory, right? So fixed load model assumes that your load is going to stay the same. Okay, no matter how much I am going to increase my what to say, my processor or the machine. Okay, so I can grow the machine. So even when in the examples that we saw, even for Amdahl's law, or any other examples that we have seen so far, we have assumed a fixed problem, right? We are going to say, hey, I am going to take a matrix multiplication of size 1,000. Okay, so 1,000 by 1,000 matrix multiplication. Now you're just going to change the processor, correct? Number of processor is going to be like in a sequential processor, it's going to be one. Otherwise, I'll choose to have 100 processors, correct? But my problem is still the same. I'm still going to run my 1,000 by 1,000 matrix multiplication on both of these processors. But that's the fixed load model. But sometimes you may not have this as the requirement. As you scale the processors, you also have to scale the algorithm. Okay, and that will be because when you want, so mostly the requirement will come from the problem side where you need more accuracy. Okay, so for example, if let us say you're trying to do some kind of image processing application, uh, then today, say, 10 megapixel could be like a good uh, resolution that you'll be okay with, but that may not be the case tomorrow, right? So then I may have to, when I increase my problem size, I also have to increase, I mean, when I increase my processor size, I also have to increase my problem size, okay, to support, like, say, 100 megapixels, correct? Or if you take frames per second as one of the metrics, today I may be okay with 20 frames per second. But when I want better performance, then I need a bigger machine. I also have to increase my problem size. I have to increase the resolution of my problem size. So I actually I put my expectation also high. My load becomes different now. Okay, so then I have to deal with like 30 or 50 frames per second. That will be my requirement. So the algorithm also changes. So that's the fixed time model. Okay, so you choose a fixed time, and then the algorithm should finish within the same given time, but my problem is going to vary. Okay, so in other words, it's going to be like on a 1,000 processor machine, I am working on 1,000 by 1,000 matrix multiplication. Then on a 10,000 size machine tomorrow I'm planning to buy, I will not run this 1,000 by 1,000 matrix. Okay, so I will be running 10,000 by 10,000 matrix multiplication. Okay, but I still have the requirement of finishing it in time, but with a higher accuracy. The third thing is your fixed memory model. And so here you see, you have your computers are always limited by memory. Okay, so now what you do is you vary both your workload as well as your time. Your time can also change. but what you're fixing is your memory. Okay, so this is like an overall model where you can so where it captures all the other factors. Okay, and then you have all, you obviously have scalability, I mean trade-off in your scalability. When you increase one, you're going to have a decrease in the other. Okay, so you have to play around with this scalability. And you see this different graph patterns to know how your algorithm or your problem behaves with increase in scaling your machine. Okay, so here this gives you the workload pattern. So this is your workload, how it grows. So you have an exponential growing algorithm here, and you have a linear algorithm, you have a sublinear algorithm, and you have a constant algorithm. Constant. This is our alpha algorithm, right? Like it's completely sequential. Okay, so no matter what, how many processors you use, it's going to stick to the same thing. Okay, so it's not going to grow at all. So the corresponding efficiency, if you find out, right? So see, look, the uniprocessor system, you almost like 100% efficiency, but as you increase the machine size, your the constant workload does it's not of any use. If you're not able to parallelize your algorithm, then it's of no use. Okay, and here your theta is your exponential algorithm, and that actually somehow keeps it up. So it's a theoretically max. So we are not dealing with any of the exponential algorithms in this course. Okay, so we only deal with linear and sublinear algorithms. So mostly sublinear is what we will deal with. Okay, so this is the ideal line, and then this is the sublinear typical line. And we saw different things like fixed memory model, fixed load model, and several other models here. So these are the different regions that we use for these models. Any questions on this? Is it clear? Okay. So we have different algorithm characteristics, deterministic versus non-deterministic. Like I said, we are not going to deal with non-deterministic algorithms. Non-deterministic algorithms, we may not have a polynomial solution. So we will not deal with those. So we will only deal with algorithms that are deterministic in nature. The next thing is computational granularity. Again, we saw this earlier. So, how much granular you want to work on instruction level granularity or uh, basic blocks or program procedure level, or it's going to be application level. You're going to choose the granularity. Then you have parallelism profile. This is very very essential. So like I said, like you draw a profile graph, right, for your application. Some In some regions your algorithms will have, I mean your parallel program will have sequential execution, and some you can parallelize it to some level, and in some places you can parallelize it completely. So different places your algorithm will have different characteristics. Okay, so your parallelism profile captures the degree of parallelism over the entire execution time. Then you have your communication and synchronization patterns. So here this says, see, even though you actually run different parts of the program in different processors, you may have to share data. Okay, so even in your matrix multiplication, that's what we saw. Even though you are doing the first multiplication part independently, then you actually have to communicate your intermediate result to some processor, and that processor is going to work on your data and calculate the next result, right? So that communication is essential. And apart from communication, even though you don't have to wait for data, you may have to wait for some checkpoints. Okay, so it's called synchronization. So ideally, you want to, it's the flow is going to look something like this. Okay, your program starts here, and then you're going to parallelize it to n processors all the way to n. Okay, and all these guys, once they finish independently, right, so they will all sync up at one point. Okay, and then they will actually sync up and then say, hey, okay, everybody's in same place now. Okay, now let's start again. Okay, so this is typically how all your parallel algorithms will be designed. Okay, so you're going to have some kind of profile like this. Okay, so this is what your synchronization talks about. Then uniformity of operations. So this one example I can give for uniformity is about your memory access. Okay, so from processing element, one, I am accessing one part of memory. It may take some time, but if I access some other part of memory, it will take some other time, right? Because it could be a local memory or a global shared memory. So depending on that, your memory access time may not be uniform. Okay, or it could be uniform if it's a shared memory model, correct? So depending on what model you have, is it like a UMA or a NUMA, your memory access is going to vary. Okay, and the memory requirement and data structures. So this is like how much memory you want, how much the memory is your parallel program memory intensive, and if so, like what kind of data structure is best for you to use. And these are some of the things that we need to consider. And there's something called as ISO efficiency, okay, and ISO efficiency function. ISO efficiency means you maintaining the same efficiency, like we saw in one of the earlier slides, right? So this is your machine size. Okay, so it goes from all the way 0 1 all the way to n, right? So maybe initially you have 100% efficiency, okay, but then efficiency is going to grow down, right? So if it's, especially we saw this for your alpha application, correct, where it's completely serial. Okay, but in general this is how your trend will be. So because always there is going to be one serial part, okay, and your algorithm will always have some portions which is serial, and then there is going to be some portions that is parallel, correct? So this is how it's going to be. So there's always going to be the serial part that forms alpha. Okay, so obviously when you increase n, your efficiency is going to come down. Okay, so this is how a typical efficiency curve will look like. However, you can work on this. Okay, so the requirement what we have now is that you have a requirement. You say that, okay, I want my efficiency to be at 80%. I'm okay with 80%. I don't want 100% efficiency, but if it is 80%, I want that 80% to be uniform. It doesn't matter whether I operate in one processor, or if I operate with 5 processors, or if I operate with n processors, my efficiency should still be 80%. Okay, so I have to model my problem in such a way that I have a constant efficiency. It's not 100% efficiency. Okay, it may be little less, but then it has to be uniform. Now once I have this uniformity, then it becomes easier for me. I don't have to worry about scaling my problem, I mean scaling my machine, correct? So if I buy 1,000 processors today, my efficiency is 80%. But if I buy another 1,000 processors tomorrow, then if my efficiency comes down to 40%, then I don't have to buy, right? It doesn't make sense for me to buy another 1,000 processors for lesser efficiency. So I will have, I need to fix my efficiency to 80%. And then I say, even if I buy 1,000 processors and I increase my problem size, my efficiency should be 80%. So what should I do to do that? Now what you can do is, you actually find what the efficiency is all about, right? So efficiency is nothing but uh, your new execution time by old execution time, right? So that is how it is. So in other words, it's nothing but your new workload by your old workload. In other words, you can say that this is nothing but your workload that is currently being executed divided by your workload with overhead. Okay, so h of s comma n is your overhead. So this is nothing but, here your s is nothing but your problem size. Okay, so the 1,000 by 1,000 matrix or something like that, right? So that's the problem size, and n is the number of processors you're using, processing elements. Then h of s comma n is the overhead we have. Okay, so now once we have this, so this is the formula for efficiency, right? So now you can actually rephrase this equation. You can actually play around this equation, and you get ws equated as e by 1 minus e times h of s comma n. Okay, so you can actually uh, get this expression by playing around with this equation here. Once you have it in this equation, this means that my workload is directly proportional to my overhead. Okay, and e, I'm keeping it constant, correct? I want to keep my e constant, so my entire e, this part becomes a constant. Then if I keep this as constant, then my workload is directly proportional to overhead. So what this says is that when you want to keep your efficiency constant, you have to focus on your overhead. Okay, so when you model overhead, then that overhead function is, it will become your iso efficiency function. Okay, so your iso efficiency function fe of n is directly proportional to h of s comma n. Now if you can model this h of s comma n, then you know that I just have to meet this requirement to maintain constant efficiency. Clear? Any questions, guys? Is this clear? What is ISO efficiency? Shubham? Okay. All right. Hey, feel free to stop. Okay. So these are all like way too abstract. Okay, and it's actually hard to grab. It's very bit dry. So just stop at any point if you're not understanding. We just quickly look at one example. Okay, so here we are going to deal with again matrix multiplication. Yeah, we are going to stick to matrix multiplication for a long time now. Okay, almost every other example we will see will be matrix multiplication. So we are taking problem size s by s matrix. Now we are going to compare four parallel algorithms. Okay, now we know that the complexity of matrix multiplication is order of n cube. Okay, where n is actually the number of processors that you are using. You can play around with this. Okay, you can have you can have in lesser than n also, but then your algorithm will change. Okay, so first we are going to see Fox Otto Hay algorithm. So according to this algorithm, they have modeled their overhead function to be of this equation. I mean, this expression here. Okay, h of Sn is big O of n log n plus s squared square root of n. Okay, we don't care how they got this. So you can look into their paper to find that out if you are interested. But that's not the a point here. Okay, what we are trying to do is we are trying to find the iso efficiency. Okay, now for ISO efficiency, what we need to do is your algorithm, right? O of S cube, that should be same as your overhead. Okay, so that's what, because they're directly proportional, right? So you want to keep your O of S cube, your problem, your workload, same as your overhead. So if you have this, then you will have your constant efficiency. Okay, so now if you think about this, then your O of S cube should be equal to O of n log n. So that's how your big O works, right? O of x cube equals to O of n log n plus s squared n, right? So then you can also say that it is O of n log n. Okay, then you also have O of s same as square root of n. Okay, why? Because O of s cube is equal to O of s squared square root of n. Okay, so then your O of s becomes O of square root of n. Okay, big O of square root of n. So these two you have you can actually infer from this one expression here. So then you can simplify this equation to form big O of s cube is same as big O of n to the power 3 by 2. Now this is the iso efficiency function we have. Okay, so this is what we need. So we need to simplify this iso efficiency function. Okay, so we just keep this in mind for now. Then we have one more algorithm, Bernstein's algorithm, where they have this overhead function and this is their iso efficiency function. Okay, with O of n squared. And similarly you have Gupta Kumar algorithm and you have Deckel, Nassimi and Sani algorithm. Okay, so you have different algorithms with different overheads. Why they have different overheads is because each of them assumes certain hardware requirements, certain network connectivity. Okay, and so on. So because of all these there are different overhead associated with these algorithms. Okay, and hence different iso efficiency function. Okay, so now if you put a tabular for this, so this is how it's going to look like. So the ISO efficiency function for these algorithms are here, and their range of applicability is given here. Okay, so this algorithm assumes that your n is between 1 and s squared. Okay, so that's your hardware requirement. When you're working on your problem, you need to have a machine of size this n, okay, satisfying the particular problem size. And they also assume a target machine. Like I said, they're going to say this algorithm will work best in square root of n by square root of n torus, and others have assumed hypercubes. Okay, so this is what the underlying assumption, and these are the different properties of this algorithm. So what we can infer from this is, so Gupta and Kumar's algorithm, so they have when you have extremely low synchronization overhead for your hardware, then this algorithm does not perform well. Okay, so when you have low synchronization, then it's not good to use this algorithm. However, for your Dekel, Nasimi, and Sani, for the given range, right? So n between your n between your s squared and s cube, and this algorithm works best. And then your Fox, Otto, and Hay, it is suitable for the range s power 3 by 2 to s squared. And finally, your Bernstein algorithm, it's suitable for anything with long communication latency, and also any range s lesser than mean range less than n less than s power 3 by 2. Bernstein's algorithm is actually good. Okay, so this is what you learn from your ISO efficiency functions. Okay, now strictly speaking, we cannot say this algorithm is better than that algorithm is better than this. Okay, so this is only a comparison between their ISO efficiency functions, and based on the range, how it is preferable. So each one have their own advantages. Okay, so keep that in mind. So that's like a mantra that you have to take with you for your computer architecture. Okay, so there is no one metric that can tell, based on this metric this is the processor that is best. So that's why we don't have like one good processor, right? Like you cannot say Intel is the best. Intel is good for certain applications. Okay, and you cannot say ARM is the best processor architecture. ARM is suitable only for certain domains, correct? Because of your application requirements, so they also vary. So we'll see one more example. Your FFT. You guys are familiar with fast Fourier transform? Hey Shubham, have you heard? Have you worked on fast Fourier transforms? Oh, you said no, right? You guys have not worked on FFTs. Yeah. So FFT is one of the famous and most it's a standard algorithm in digital signal processing. Okay, so here we don't care about what FFT does, but here you have your FFT's algorithm workload uh, modeled as big O of S log S. Okay, and when you put it on a hypercube, you get an overhead of H1 of S comma N. Okay, and so that's your expression for your hypercube overhead. And from this, you get an ISO efficiency function of big O of N log N. Okay, so that's your F1. F1 is your ISO efficiency function. Now, if the same fast Fourier transform, if you put it in a mesh, then you get another overhead H2 of S comma N, which is this expression. Now they differ only by one. Okay, one of the factors. So here it is S log N. It is S square root of N. Now we need to find which is better. Okay, so now when you find the ISO efficiency function, so here F1 has ISO efficiency function n log n, right? Hypercube has n log n. However, mesh has big O of square root of n k to the power of square root of n. So this is a bit complex. The moment you have something in exponential, that is dead. Okay, you really don't want to pursue in that direction. Okay, so that's what you get here too. So if you look at your hypercube, you have three different efficiencies. Okay, when your problems scales, when your problem scales, you have three different efficiencies. So when you have 0.66 as efficiency, so this is your problem size. Okay, and so how your sorry, this is your Correct. Problem size, and you assume different efficiencies here. Okay, so you're maintaining ISO efficiency of 0.87. So this is how your problem is going to behave. Okay, as your machine size increases. Ideally, it will be like this, right? Your ideal curve, your 45-degree line curve will be here. Okay, but so this is how you maintain your ISO efficiency. Now, when you compare that to mesh, okay, let us just take one of the ISO efficiency functions. Let's say you pick E equals to 0.66. Then your hypercube has the growth like this. Okay, however, your mesh has a growth of your problem like this. Okay, so this means that your hypercube, your problem size is not going to scale much. Okay, however, on a mesh, your problem is just going to explode. Okay, so this says that hypercube is better suited for your fast Fourier transform than mesh. Okay, so this is one place where you can use your ISO efficiency function. Any questions so far? Okay, if not, I think we're done for today. Okay, so tomorrow again is a very important topic, but hopefully by tomorrow we will wrap up this module. Okay, and tomorrow also we will follow Saturday timetable. So yeah, so if there are no questions, then we are done. Thank you guys. You can type in your USN and leave.